Hello, geometry. Welcome back from winter break. Today, we are going to be talking about our non-rigid motions. Previously, we had discussed rigid motions, which are things that don't change the size or shape of a figure, right? Those are our translations, rotations, and reflections. Now, let's talk about some non-rigid motions that are going to change the size or shape of our figure, like dilations, stretches, and compressions. We had covered this in our basics at the beginning of this unit. Learning target today, I can dilate and stretch a figure and determine how a figure has been transformed. Success criteria, today we're going to talk about finding the center and scale factor of a dilation if you are given some pre-image and image points. And we're also going to look at some coordinate rules. Pause if you need to. Okay, what exactly is a dilation? It's going to be a transformation that changes the size of a figure by the same amount in all directions. All right. For example, here's a little apple. We're going to work with this apple here. So this is your pre-image, right? Regular sized apple. If you do a dilation by a factor that's greater than 1, that means, and you'll see in just a second, that means we're going to take everything and multiply it maybe by 2, or multiply it by 3, right? We see that it's changing the size. It's not changing the shape of our apple, but the size itself is getting bigger, right? So we're getting bigger in all directions, vertically and horizontally. So may want to write down a little thing. If you're doing a dilation by a factor greater than 1 equals bigger. If you're doing a dilation by a factor that's less than 1, maybe you're taking your pre-image apple and you're multiplying it by 1/2, right? That would be a dilation by a factor that's less than 1. So your figure is going to get smaller. Or maybe you multiply by 3/4, right? 3/4. That's a number that's less than 1. So your apple's going to get smaller, all right? Pause if you need to. A stretch, something that changes the shape of a figure by a factor greater than 1. So we looked at dilations, getting bigger or smaller, but specifically, we're going to look at changing the shape now. So what if we do a vertical compression or a vertical stretch, all right? So just make sure you understand what stretch and compressions are. Again, stretch by a factor greater than 1, like multiply by 2 or multiply by 3. Compression changes the shape of a figure by a factor. It's got to be greater than 0, but less than 1, right? 1/2 is obviously greater than 0, but less than 1, but our figure is going to be compressed. So look at the examples. We have our pre-image apple, right? The regular apple. We can see here that we've done a vertical compression because it got smaller. But notice that the width of my apple did not get smaller either. We can see that the width of my apple is about the same size as this image, right? The only thing that changed was it got smaller. So this is a vertical compression because we took our vertical height, multiplied it by a number that was greater than 0 but less than 1, but the width is still the same, right? Now take a look at your horizontal stretch, okay? Horizontally, obviously, this apple got a lot bigger, but the height didn't change, all right? So in our previous example, again, the height changed because it was a vertical compression. But here, if you're thinking horizontally, we stretched it horizontally, so we multiplied by a number that was greater than 1, but it's only a horizontal stretch because, again, the height of the apple, and if you look, say that's probably the height of the stem, about the same size in my image. The bottom here, about the same size, right? But again, that width of my apple changed. All right, pause if you want to maybe get a sketch. Okay, I've got a little picture here, Jack Skellington again. So we'll just kind of get another example. Boom. That is a horizontal compression, right? His height didn't change, but he got a lot skinnier, so that is a horizontal compression. This is a vertical compression. All right, again, we see that his height got a lot smaller, but his width was still the same. Okay, what about a horizontal stretch? Again, height is the same, width got a lot bigger. I stretched him out horizontally. And then how about a vertical stretch? Don't really have too much room, but there we go. He got a little bit taller, but again, his width didn't change. But if we do a dilation, I'm going to drag that guy in the corner here. Now, his height and his width changed. All of it changed. It got smaller. This was a dilation by a factor that was less than 1. So the distance changed in all amounts, right? In all directions, excuse me. If we wanted to dilate him to get bigger, there you go. All right, Jack Skellington, thank you very much for your service. Okay, how about a center of dilation? So when we dilate, right, and that's changing in all directions, we have to have a fixed point in the plane that's not going to change when the dilation is applied. When we see our coordinate rules here in just a second, our center of dilation is pretty much always going to be the origin, all right? We're going to be dilating away or to the origin. When we dilate or when we stretch or compress something, we need a scale factor, right? I kept saying multiply by a number greater than 1 or less than 1, greater than 0, right? We need some sort of scale factor. To find the scale factor, if you were given an image and a pre-image, you would just need to take the ratio of the length of a segment on the image to the length of the corresponding segment on the pre-image. Again, what I have in blue is really what you need to write down. So a scale factor is the ratio of your image to your pre-image. All right. Take a second, pause if you need to. Let's look at an example here. I've got 2 different ways that you could think about this. So usually we're going to think, and with our coordinate rules, our scale factor is just going to be a general parameter. It's just going to be k. We're going to call it k. All right. So we can see that k, our scale factor, is this ratio between, let's say we had a segment ST. So you see how S prime and T prime are in the numerator of this ratio. So we're looking at the ratio between our image to our pre-image. All right, so that's using some general letters, or I would get this part down. Scale factor is equal to image over pre-image, right? We have that ratio. Maybe it's length of a segment, right? Maybe it's coordinates of a point. Scale factor is the ratio between your image and your pre-image. Pause if you need to. We're going to use this here in just a second, this little like formula. Okay, so again, you just wrote this down. Scale factor equals image over pre-image. For example, let's say that your image segment is 8 centimeters, right? That's the segment after the transformation. Your pre-image, your original segment was 4 centimeters. So your scale factor is, well, scale factor has to be your image over your pre-image. So I'm going to take that 8 centimeters, divide it by my pre-image, which is 4 centimeters. 8 divided by 4 is 2. Scale factor here is 2. And that just kind of makes sense. If you started with a segment that was 4 centimeters, you multiply by 2, obviously your image is going to be 8 centimeters. Okay, maybe looking like a lot, but pause if you need to, get some coordinate rules down, and I'll start to break this down here in just a second. Okay, so dilation. We are changing in the same amount in all directions. We see that we're taking, again, this is, I said the center is always going to be the origin. For a dilation, we're going to take a point xy, and we're going to go to kx, comma, ky. So again, I said k is usually our ratio, our scale factor. So we're going to take that scale factor, maybe it's 1/2, right? We're dilating it smaller. Or maybe it's 5. We're going to get a lot bigger. You're taking that scale factor and multiplying it to both of your coordinate points, x and y. For a vertical stretch, again, stretch means you're getting bigger. Your scale factor k has to be greater than 1. It's going to take a point, x comma y, not going to do anything to the x coordinate, right? Think about x coordinate is like your x-axis, right? That's horizontal. So vertical stretch is going to change things vertically. So we're going to take our scale factor and multiply it only to the y value, all right? So same thing with a horizontal stretch. You're going to take your scale factor where k is greater than 1, and you're just going to multiply it to your x coordinate only, right? That leaves your y coordinate, that leaves your height. You could think about that. Your height remains unchanged, but your x coordinate, the horizontal movement, right? That is going to be stretched. Same thing with vertical compression or horizontal compression. If your scale factor k is greater than 0 but less than 1, you're going to be compressing. If you're going to be compressing vertically, then you're going to multiply your y value by k. If you're going to be compressing horizontally, then you're going to multiply your x value by k. All right? Pause if you need to. Let's look at an example before you come to Blackman 107 to review with us. Let's take this triangle, the red one that I have graphed on the plane, and we're going to stretch it vertically by a factor of 3. So we have that scale factor. What I'm going to do is I'm going to just put my points out there, right? So we can see the coordinates themselves, and then we can graph it on the plane. So we have 3 points of our triangle here. I have those pre-image points listed. If we wanted to find our image, let's go look at our coordinate rules and see what it tells us to do. So, and you should have this in your notebook, right? Stretch vertically. K is greater than 1. So 3 is greater than 1. All right. What I'm going to do is I'm going to take my coordinate points, x comma y, and go to x comma ky. So the only thing I'm going to multiply by is 3 with my y coordinates. All right. X coordinates are going to remain unchanged. Again, this is a vertical stretch. We're not changing the width. We're only changing the height. So I know I only need to multiply my y coordinates. So my image points should look something like this. Again, I see that my x coordinates, 1, 2, and 3, right down through those remain unchanged. But my y coordinates, which were -1, 2, and -1, well, -1 times 2 is just, or excuse me, -1 times 3 is just a -3. 2 times 3 is just 6. And then once more again, we have -1 times 3 is a -3. If I plotted all those points, now in blue, we see the image of my triangle after my vertical stretch. Obviously, this thing got stretched. The width is still the same. Everything just got stretched vertically by a factor of 3. And it's getting stretched away from the x-axis only, right? Okay. Pause if you want to get an example down. We'll go over some more of this as well. I will see you in Blackman 107 for some review. Thank you, guys. Glad to have you back.